Hello, everyone. Today it's my pleasure to talk to you about the upcoming Marc 2013 release. This is a very exciting release for MSc and with lots of great capabilities. And we expect that it's going to go out any day now, and you will get, those of you who are existing users will get an email when it's available to download from the SDC site. So what we have basically is we have 5 basic themes that we are looking at: ease of use, contact, fracture and durability, rubber analysis, and multiphysics. And I'm going to go in that order and drill down a little bit on the new technology and changes that you will observe in this product. The first thing is there's an improved contact definition. We've been listening to the customers for many years, and initially contact started out, people would have just a few parts in their models, often for manufacturing analysis. But now, effectively, they're doing problems such as assembly modeling, where they have many more parts, and I've seen problems with hundreds of parts being used with Marc. So we needed to come up with a new input, new GUI to support these problems. So the goal is really for, as I say, problems with many bodies associated with them. And I think everybody's familiar with the way we treated contact table in the past, and knew that there's a limitation when there were more than 15 bodies. You had to do scrolling, and it was a little bit painful to do. So now there's a new contact table option, and within that contact table option, there are multiple ways for you to look at your data and to enter your data. So the default one is very similar to what we saw in the past. It's called the View Mode Entry Matrix, and we see that it's the same. You would basically identify what's touched or what's glued. We'll see a little bit later that it's not quite the same, but the key message is there's a new button called Show Visible Bodies Only, and when we activate that, we can basically say, rather than look at all 100 bodies, we can say, well, we're interested in the interaction of parts in this region, so let's just focus in on a few bodies, and in which case this table will be reduced in size. And that helps you in the work that you need to do. And that's shown right here. We basically have activated the bolt, the pin, in the insulation, and in which case, effectively, what we see is rather than a table being 8 by 8, it would be just 3 by 3. And it helps on the visualization of what you are currently working on. There's another format to this, and it's called the entry list format. And the entry list format is going to list all the different contact bodies by the pair, by the interaction that has been set up. What's the first body? What's the second body? And then note that it introduces a new concept, which is what we call an interaction property. And that interaction property is going to contain information like the friction coefficient, the heat transfer coefficient, the separation stress. And if you have many bodies and they have the same type of interaction properties, one needs to just define this once, and one can reapply this over and over again. And of course, if it's not relevant, if we have symmetry bodies, we know the detection method isn't particularly relevant, and it will just say not applicable for those particular cases. The other way is something known as the body examination, and when you look at things from a body perspective, you will identify what is the featured body, namely, in this case, the bolt, and then it will just list those bodies that are interacting with this particular bolt. And we'll see later on that we have a new picking capability that makes it easy to identify the contact pairs between the bolt and other bodies. So there is this new concept of contact interaction properties. You're going to get to learn to love this particular menu because effectively what we're doing is we're using the contact table really to represent the geometric relationship, and we're using this contact interaction properties to represent the physics relationship and the numerical relationship between the different bodies. So in this case, it's between a mesh deformable region and another mesh deformable region. We have other concepts in terms of new body types, and I can't go through all that, but I refer you to the release guide that comes with the product, and it will talk about that in greater detail. And of course, this menu would in fact allow you to go to the friction region, go to the separation region. And that's shown here, so it looks a little bit scary, but it's really not scary at all. So here effectively there were really four different types of contact interaction properties. You would have basically gone from your contact table, in this case an entry list, to the interact one properties, and then whether or not you need to set the separation, the friction, the wear, or in the case of segment-to-segment contact, the additional augmentation parameters, you would have effectively added more detail to the simulation as necessary. And all that would have been grouped together with the interaction properties. And as I mentioned earlier, in this mode, and this is one of many modes, that if you would have identified it, that the feature body was bolt, and you said, I want to connect the bolt or potentially contact the bolt with other bodies, you could either pick them by looking at a list, or you could simply pick the body. So if you would pick any surface, it would recognize all the surfaces that were identified in that body. It would pick that body. If you picked an element, it would figure out which body that belonged to, and it would identify that body. So it improves the ease of use. Again, often you're zoomed in on a particular location, you're focused on that, and it's easier to do these things with graphical picking. As long as we're talking about MenCat, I'm going to talk about quickly a few other things that are in MenCat. We have updated our CAD import capability using CAD Fix version 9, and that's allowed us to access the newer version of ASYS, newer versions of Unigraphics, newer versions of Pro-E, SolidWorks, Inventor, etc. In terms of CATIA, we continue just to support CATIA V5. That has to do with the relationship with the Dassault organization. One of the things that people said about the new MenCat, as opposed to the classic MenCat, is they missed the middle mouse button for help. So we've brought back the middle mouse button as a context-sensitive help system, and we've made it better than ever so that the help files are basically in HTML format. We took all of our old help files and we converted them to the new format. And additionally, for newer capabilities, we're slowly working to replace all the help files with more engineering value, including graphics in these files, keywords effectively in bold, which you can then cross-reference with, images that I mentioned, and this cross-referencing capability. So as everybody knows, documentation is a large process, and so we will continue to improve the help capability. Another feature that people often work with is they have their pop-up menus, especially if you're in a dual screen configuration. You spend a lot of work to organize it, then you leave Mentat, you bring back Mentat up again, and you have to spend the time reorganizing your menus. But now what you can do is you can save the location of those pop-ups, and when you start Mentat again, it will basically put Mentat back in the same state that it was before. Another Mentat feature is enhanced renumbering, and this is in two respects. One is you can start your renumbering at any given level, but also you can renumber on a region-by-region basis. So you could have this shaft starting with number 10,000, and this region to start with number 1, and this region to start with number 20,000. And that's very common in certain industries where multiple users are working on the same model. Finally, I want to talk about something called global quantities. Of course, we have had global quantities for a long time, but from the results menu, there's a new pop-up that's called global postcodes. And what this does is it contains things like the energy, it contains things like the volume, it contains things like the iteration number, and you can basically bring this up, and if you were basically in monitor mode, this would be continuously updated during the analysis, and it's a quick way to see how the transient behavior is occurring. So those are the changes really in core Mentat. So let's talk about some of the things that are in Marc. And the first one I want to talk about is something called multi-stage. Sometimes we call it multi-stage. Sometimes we call it sectioning. But it really has to do, it was designed to deal with manufacturing problems where you typically have a multi-stage type of analysis, and you want to basically do something like look at the sheet, then do a first stage analysis, do your punching operation, then you want to look at your results, you might want to change the tools, and then do a second stage analysis. So what this sectioning capability does is it allows you to define a part or a set of elements with initially a given material as a section. And then during these different stages, we will create a section file that has the associativity between the model and the results. So this is an alternative to using the restart option, and it keeps this close associativity between the parts. So you could have multiple section files, and each one of those section files would have the results associated with them. So it's really fully contained, self-contained model, and you can create one of these, and then in the subsequent analysis, you can import that into Mentat, and wherever you used to see things like a contact body, it will say something like add elements, or it will say add an existing section file, and that's effectively what this is referring to. So in this little example, we have some material here. We would have defined the material behavior. We would have defined the geometry. We wouldn't have done any simulation. We would have gone into the job menu, and use the model section to create such a section file. And it would be initially it would just be the geometry, the connectivity, the coordinates, the material properties. Then in our second step, we would basically import that model section file, and we would then apply everything else to it, contact type boundary condition, put in our convergence control and other issues. And you notice when we imported the file, the section file, we no longer see the elements. We no longer see the node IDs, because this section file has now been previously defined. In this portion, you cannot modify an existing section file, the geometry of the section file. We would do the analysis. We would basically output or export a new section file, and then we could take that section file and use it in a subsequent analysis. We could also take that section file and expand it from an axisymmetric model to 3D type model. So in that regard, it behaves like the pre-state option. So the pre-state option worked off the post file, then we still often needed our restart file. So this basically operates off a new set of files that are called the section files. Another general ease of use enhancement that we did was improving the dynamic capabilities in Marc. So as everyone knows, over the last few years, we've had some significant dynamic events, earthquakes, other types of failures. Marc was not as sophisticated as other products, including our sister product, MSC Nastran. So we've effectively put in more technology to deal with dynamic events and to deal with spectrum response calculations that are utilized in the civil engineering community and in other industries as well. So we expanded spectrum response to include not only giving a density function as a function of displacement, but velocities and accelerations, the ability to give different spectral input in the different directions, new technology or new techniques for combining the modes and for applying damping, new output quantities, and new ways of controlling the number of modes in the system. So just representative, you could have had a problem like this and basically say that the vertical displacement and the horizontal displacement are a different density function with respect to frequency. That's very typical process. You can also have the spectral input to be a function of the damping ratio, which is also common. So if you basically have applied damping to your modes, it will utilize that in the subsequent spectrum response calculation. Another nice feature is what you can do is you can say, I only want 3 modes to be applied in the structure, and it will determine what the modal masses of each one of those modes are, and it will determine that 40, 70, 10%, 80%, so I have a missing mass of 20%, and it will compensate the results for the fact that your modes are not using all the mass in the structure. And on the flip side, if you had a lot of modes, you could basically say, well, I only want 70% of the mass to be included, in which case it would just use these first 2 modes, 40 to 30%, and it would effectively ignore that mode when doing the calculation. Of course, spectrum response, like all the other capabilities associated with Marc 2013, is fully supported by Mentat, so that you can either select the mode of your spectral input, or give different factors in the different directions and other features as well. The other capability, which was a small hole in the program, we used to not allow a user to apply a fixed acceleration when using table formats and harmonics. We have closed that little hole. We've done a few other things for harmonics that we will talk about later. The last thing I want to talk about in terms of ease of use, there's a capability called advanced thermal analysis. It used to be only supported by the classic MenCat. It's now supported by the new MenCat look as well. This advanced thermal analysis is designed for doing problems of pyrolysis, typically in thermal protection systems like rocket engines or furnaces, and for looking at ablation. Ablation is used in a lot of applications, including brakes and other things as well. There are some additional capabilities that were added to this in the 2013 release, but I don't have time to go into them today. So contact, of course, is an important technology. We always say you've got to have a little bit of contact in your life, and this is an area that we focused on, and we have produced a lot of interesting technology with this release. The first one I want to talk about is interference fit. Previously, the interference fit could only deal with small overlap of the particular bodies. It was limited to being within the size of the contact tolerance. We've added a new capability that allows you to have much larger overclosure, either due to geometric irregularities or due to really true design. And in this case, it's a still relatively simple problem of a shaft in two different plates, and we can determine the deformation. But the real motivation for this capability was really in problems where the mesh was significantly overlapping one another. And that might have been due to, an issue with the CAD model. It might have been due to an issue with the meshing. It might be because you decided to change your design but did not want to go back and redesign everything. So in the case of these two O-rings, this is very large penetration. And previously, of course, we would have said, oh, it's too bad. It's over the contact tolerance. There's nothing that we can do. And of course, now we can do something better. First, we'll show it in 2D. Effectively, what it does is you basically say that there's an interference between these two bodies, and you say, how do you want the interference to be resolved so that these two parts are not penetrating one another? You'll notice one of the big differences is that this no longer is done in just one increment, so it's done over multiple increments. It can be done either with fixed time stepping procedure or adaptive time stepping procedure. So there's this new button called interference fit, and effectively what that does is that leads you to new pop-up menus that allow you to define how you want this to be resolved. And you basically can say, move the body so in the normal direction to the other body, or in this example, what we're saying is to scale the body down in size about a particular point in a particular coordinate system. And the key thing is we're going to do this over multiple increments. So we want things to be driven by a table that effectively goes to zero overclosure at the end of the analysis. So that seal that we saw earlier, which had significant overclosure at the end of 10 increments, we see that we have nice contact, no penetration occurring. This works both for node to segment and segment to segment contact. And for these classic problems of interference of shafts, again, this initial distance is much larger than the contact tolerance distance. We are able to easily solve these problems. We can even do rather crazy problems. This is kind of a ring where initially it was on the inside, but we really wanted the initial conditions to be on the outside, and we basically can expand the inner ring to be now in contact on the outside with the outer ring. Another example, even though it's geometrically trickier, basically we'll move these two grooved surfaces, and on the left side you see the displacements, and on the right side you see effectively the stresses that are generated, and then in a separate step you can bring stresses down to zero. The second part of contact I like to talk about is beam contact. And the beam contact is really very exciting new technology. We had beam contact before, but it was rather limited in scope. And this one has been originally designed for a few applications. It's been designed for the drilling industry, where we kind of have a pipe within a pipe. It's also applicable to Bowden cables, such as you have on your bicycle, but of course in your car brakes as well. And it's also geared to the biomedical industry, whether or not you have angioplasty or inserting a stent. And of course, it's also applicable to civil engineering and aerospace structures, as we'll see later. So it effectively works with open section beams and closed section beams. Important to recognize these are still beam elements, 2 nodes per element, 6 degrees of freedom, but we're capturing the exact geometric representation of the beam. And when we do contact, we will effectively do the contact between the true representation of the beam and another beam, or the beam and a shell. So one can observe here we have basically an I-beam contacting a shell, multiple I-beams as stiffeners. We have here a couple of beams below, simple beams. Here we have square section beams. Here we have a beam within a beam. And we can include beam offsets. We can include shell offsets. We don't need to do any RBEs or any sort of complex equations. You notice that the mesh of the I section is different mesh than my plate structure, and it all comes together. So typically for this problem, you would probably have used glued contact between all the beams. This is what the original design was for. We see here a pipe within another pipe, and it is making true geometric contact based upon the configuration of the pipe. And of course, initially it was for this case, but we did obviously the external beam contact as well. Other examples are twisting cables. This is one of my favorites. This is the coil. I'm just showing initially the coil as the beam elements. We're seeing the beam contact, and if you look closely, you see effectively there's some buckling going on when we overclose this coil. And if we look at the 3D representation, this is what we see. So rather than having to do a 3D solid analysis with many more elements, we can do this at a reduced computational cost using beam elements, but still getting the accuracy. And this works in dynamic analysis as well. This would be a typical arrestor that you might use to catch something. And of course, the 3D representation of these beams and dynamic behavior as well. Of course, it's all supported by MenCat. Basically, when you're in the beam menu, you would say that you wanted beam contact, and you could specify, you know, if it's a circular pipe, you could say whether or not the contact occurs on the outside and the inside, or just the inside or just the outside. This works only in conjunction with segment-to-segment contact. The next thing that we did in this release in terms of contact is we, for the last few years, we've been growing the capability of the new segment-to-segment approach. We believe that the segment-to-segment approach is effectively more accurate, and it's easier to use because you don't need to define a master surface and a slave surface. It didn't work before for multiphysics, and now it works for heat transfer, thermomechanically coupled analysis, electrostatic and magnetostatic. And we can see even on a very easy model, the node to segment, if these blocks were not regularly spaced, we'd see a little lack of accuracy in the solution. And with the new method, we see a very accurate solution. It can be applied to very complex problems, such as this jet engine blade sitting in this fir tree to get the thermal conduction between the two different parts. As I said, it's available for all the different multiphysics that is available in the program. Here we see it in magnetostatics. Later on, we'll see an example of it with magnetodynamics. Finally, we're going to talk about adaptive meshing with contact using the segment-to-segment procedure. This was a beta feature actually in the last release for 2D. Now it's available for both 2D and 3D. It's of course highly relevant for those in the manufacturing industry or in the rubber industry where there are large shears, and those shears result in large amount of deformation. And again, one can use it in conjunction with the segment-to-segment procedure, which automatically does double-sided contact, which results in greater accuracy. So it's easier to visualize in 2D, but the capability is, of course, available in 3D as well. Using the tetrahedral elements is the most natural choice in 3D analysis. Finally, there's one last piece of contact technology that's been introduced. This looks like an academic problem, but we can associate a node to a rigid body, and so now we can actually do rigid body to rigid body contact. The actual application is really, again, having to do often in manufacturing processes. You want the process to stop when a particular tool comes in contact with another tool, and this can be easily modeled with this rigid body contact with node option. So I want to move on to fracture and durability. This was really, of course, the birthplace of nonlinear finite elements, was really having to do with fracture analysis, because, of course, nobody wants any failures in their life. And we have done really two things in the 2013 release. The first really has to do with crack initiation. where we have new methods to introduce a crack into an existing structure, and we have new methods to basically go from a structure and utilize the delamination criteria to generate a crack, and then later on do the propagation. So first, looking at the initiation, what you can do is you can take an existing model and you can hypothesize the location of the crack. And you don't need to regenerate the mesh. You basically say, I have a little surface crack here, or I have a through and through crack over here. And what we'll do is we'll use our adaptive meshing capabilities to generate a crack in that location. And let's say on the next day you wanted to rotate the surface crack. You could rotate the surface crack, and you wouldn't need to regenerate the mesh of this particular region. So it's a useful feature. There are some menus that when it talks about crack initiators, and then talks about doing remeshing, and then you would say insert a crack in the body. You'd define what your body was, and you would define what the geometric representation of the crack is. And the geometric representation of the crack comes through a faceted surface that is generated by Mentat. And once you did that, later on you would assign a template crack to it, which we'll get to a little bit later. The second thing we really did in terms of fracture mechanics is we improved the process and the accuracy of using VCCT with higher order elements, particularly with tetrahedral elements, so that we get a more accurate solution. And then we've introduced these two methods for crack propagation in 3D. One is cracking along the faces of existing elements, and the second, which is the more powerful, the global adaptive meshing. So when we crack along element faces, we can do some specifications. We can say, hey, you just go crack and base it on the direction of the VCCT, or you could say only allow the crack to be between different materials. It's much more general if we do the global remeshing. And with the global remeshing, of course, we can say we can have single crack, we can have multiple cracks. It's a very general capability. So here's our first example. This is really a penny-shaped crack in this body, and we're basically going to be applying a tensile load, and that penny-shaped crack effectively spreads. Everything is uniform, so it effectively remains reasonably planar in the model as the remeshing occurs. The amount of crack propagation here is governed by Paris's law. Here we have an example. This is a simple mesh. We'll show something similar later on, but this is effectively saying propagate the crack along the existing faces of the elements. There's no remeshing occurring in this type of model. Here's an example where we have effectively a composite plate. We might have two different materials, and effectively as we pull this, it effectively unzippers in like a mode 1 type failure along either element boundaries or along material boundaries. Here's another example where we use these things in conjunction with one another. We're basically saying that I have a T connection, a T beam, and it's basically bonded to this plate, and the plate happens to be bonded to this bottom surface. I'm going to pull up in this direction. I'm going to use the breaking glue option to start a crack. So as soon as the breaking glue says there's no more contact, it forms a crack surface, and then I'm going to use that information to propagate the crack. So this is the other approach. This was basically using selecting element faces, but it works in either case. This, we've removed these elements for clarity. Two cracks get formed, and then effectively as we pull up, we see those crack surfaces, those crack fronts propagate, and we see the delamination between the T-beam, T-section, and the bottom plate. In general, generating cracks and using the adaptive meshing capability is the most general, as we see here, and what will come up to later is how the meshing is done to effectively do this. You can look at things like the strain energy, and of course the strain energy drops after the crack is created, or you can look at the forces on the bodies, and again the force is reduced after the bodies crack. And this occurs with, we see whenever we do adaptive meshing, we're using tetrahedral elements. We can either use the simple tetrahedral elements if this is elastic material, or we'd be using element type 157 if this was an elastic plastic material or a rubber material. The fracture mechanics capabilities are available for any material model. The question is really whether or not something like the Paris law is an appropriate method for determining what is your crack growth, or is looking at the energy release rate versus the critical energy release rate, whether or not that is applicable to different material models. And here we see the propagation of the crack front from that previous model. This is basically the same tearing problem, but now, of course, we start with a finer mesh and we do remeshing during the analysis. Again, Mentat-wise, we have all the menus to generate the data to introduce for this. We basically say that we're going to use remeshing for our crack growth method. The crack growth increment, in this case, could either be based upon a user-defined size or a user subroutine or Paris law. When we determine that initial crack motion, we can base it on either the energy release rate versus the critical energy release rate, or we could look at different modes, or we could use the Reader mixed mode theory. Well, this need of fracture mechanics and things we do in manufacturing has drove us in another direction, which is to improve the adaptive meshing capability. And the idea is to improve it such that you have a greater control over the mesh density in your system. And that mesh density can be controlled by almost anything. Here what we did was we did an analysis and we said we're interested in the plasticity, so we pulled this plate with a hole. We generated these typical slip lines, and based upon that plastic strain, it would then generate a finer mesh in that particular region. We can also generate a finer mesh based upon curvature control. We can generate, this one was done based upon the equivalent stress, where again, where the equivalent stress is larger, we'll have a finer mesh. The more critical thing is where things are not interesting, you can therefore have a coarser mesh, so you can have a more cost-effective solution. This is available for shells, for triangular shell elements or quadrilateral shell elements or for tetrahedral elements in 3D. It's available for not only structural analysis, but heat transfer analysis, or in this case, an induction heating problem, where we have extremely fine elements, where we have high magnetic flux, and then, of course, when we look at the general air, we need to do coarsening, otherwise we have really a computationally prohibitive type of analysis. We are forging simulation, so we might have defined this region, and we could say remesh or give me a higher density based upon the region, or we could say give me a adaptive meshing based upon the plastic strain. So if you have something like criterion based upon stresses, and if you had a body and it had a high load in one location, you get a high fine mesh density there. If that load would move, those elements would get bigger, and perhaps in some other region would be the high stress area, and then the mesh would be fine there. And this really allows us to do models that we had troubles with before. This is obviously a very large deformation problem of a rubber material using the segment-to-segment contact procedure and a combination of using a box method and again, for fracture mechanics, what was done here, the key word is you want full mesh density control. You specify a particular distance. You specify what you want, all the cracks in the body, and it will give you a finer mesh around the crack. And as the crack propagates, you will continue to get a finer mesh in the vicinity of the crack. There are lots of different criteria. The ones that I like the most has to do with the element quantity. All the element quantities that are available through the post-tape option you can utilize here. Of course, there's also a user subroutine. So we won't go into the subsequent menus here, but there are lots of options that you can use. Just want to move over to the last part of the durability section, which has to do with metal damage. There's a new model. It's called the Bonera Metal Damage Model. It's similar to the Gerson model. It can represent void generation, growth, and coalescence. When things damage, the only thing that is influenced is the Young's modulus of the material. It's easier to use than the Gerson damage model because it requires less material data to use it. So in this problem, you can see it's similar to before. We see effectively the slip lines. That's where the damage occurs. When the damage reaches a certain level, the elements disappear, and eventually we see this rigid body mode develop in the structure. So let's quickly move over to the area of rubber, a very important topic. We have introduced viscoelastic behavior, another viscoelastic behavior model with our rubber models. It's known as the Bergstrom-Boyce model. The Bergstrom-Boyce model can be combined with all of our different rubber models, Mooney-Rivlin, Ogden, Aruda, Boyce, and Gent, and it can also be combined with damage as well. Effectively, what you can think of is you can think about in a small displacement world, even though we don't have small displacement, you can think about a rate-independent portion or the long-term portion, and then you can think about the rate-dependent nonlinear behavior represented by the dash pot. In a large deformation mode, we talk about deformation gradient being divided in a volumetric and deviatoric part, and then we take that deviatoric part and we divide it again in terms of a rate-independent portion and a so-called viscous portion to get our complete contribution. Effectively, what this means is if I take my nonlinear material model, and if I would load it up and then I would hold the strain, this is a displacement controlled problem. What we see is we see stress relaxation, then we load it up again, we have stress relaxation, etc. during the whole process in both the loading area and the unloading area. Combining it with other things, we can think about the first being pure Ogden, then looking at Ogden and damage, then we could do something that would be Ogden and Bergstrom-Boyce, and then we could think about Ogden damage and Bergstrom-Boyce. And what you see is effectively all these modes result in the material being softer than if we would have used the pure Ogden mode as well. Again, basically what you'll see is in the models of the material Ogden, you'll see a button viscoelasticity that existed before, but now you have a choice, and the last one we'll get to later, and you would activate this Bergstrom-Boyce model, and you'd enter the parameters associated with what looks like a Rudder-Boyce type model. Next one is frequency-dependent damping, very important in the automotive industry. You have a bearing, you basically are using it to insulate the noise between the engine and the frame or in the suspension system. It has a rubber material. The rubber material, as we just mentioned, is viscoelastic. That viscoelastic leads to frequency-dependent damping. And but there are also applications in civil engineering as well. And what we do is we can think about if you would do a test and you looked at the storage modulus, that contributes really to the stiffness. The loss modulus contributes to the damping. So we had a capability before, actually for the almost close to 30 years. It was called phi coefficients. It was based upon Ken Moorman and Knoll model. It was very limited in scope. So the new model is much more general. It can be used for either total Lagrange or updated Lagrange, and with all the conventional rubber models, and it can even be used in conjunction with thermal-rheologically simple materials. Again, it's a very similar menu. We're looking now here at Mooney, and we see the viscoelasticity, but here, rather than specifying the Bergstrom-Boyce model, we might either ask for a Prony series, in which case we have to give the coefficients, or we might directly enter in the storage modulus and the loss modulus, in which case it will figure things out. So the figuring out the Prony series, this is achievable with Mentat in the same manners that we did before. So here's a little example. It's we basically have a bushing here, a rigid outer cylinder. We're going to basically pull in this direction and then apply an excitation. From the pulling, we basically would have gotten a rubber shape like this. And then after doing the excitation here between 0 and 100 hertz, we would have looked at the displacement as a function of the frequency, and the phase angle is a function of the frequency, and the amount of dissipated energy or the dissipated power as a function of frequency. Last rubber model I want to talk about is the Marlow model. The Marlow model is a simple, easy-to-use model. The user basically enters the stress-strain law. You don't need to determine the coefficients. We will use the stress-strain law directly. The advantage of this is if you also have temperature-dependent material properties. But the downside is you can only enter in one set of test data, either uniaxial data or biaxial data. So if you enter the one or the other, then we know from history that the model might not represent other modes of deformation very well. So it's not as sophisticated as, let's say, the Ogden model if you enter in multiple test data. Finally, I want to quickly talk about induction heating. Induction heating is something we've had before. Now we've combined it with structural analysis. Typical applications are in manufacturing or in heat treatment or in problems where you want to control very accurately the temperature on the surface. And by controlling on the temperature on the surface, you can do things like case harden the material. This is done using a harmonic electromagnetic analysis or a harmonic magnetodynamic analysis. And effectively what we're doing is we're doing a three-way coupling between the harmonic problem to calculate the flux, the heat transfer problem to generate the temperature, and the structural problem. So here we see a coil that moves down this bar, and effectively what we can get out the temperatures generated. Those temperatures, in fact, generate an axial thermal strain, which would in turn generate a stress or a residual stress. An additional thing that we added was what we call the dual mesh mechanism, and this may be expanded to other applications as well. We'll show the example. It's 6 coils, and something is going to move through the coils. In the formulation that we had before, we'd have a single mesh, and then this is all air that we would need to remesh as this billet would move through. The new method is we use 2 meshes. One is a mesh that's fixed in space and another mesh that represents the solid that moves through. We use contact to differentiate the near effects and the far effects. And if we look at the magnetic induction between these 2 mechanisms, this is using the single mesh approach. This is using the dual mesh approach. So here we don't see a fine outline of the billet, but the induction is the same. And if we look at the temperature distribution, here you can see that the temperature distribution is the same. Here you see the air is being continuously remeshed. Here the air is not being remeshed. And finally, the last thing I want to mention is we're continuously working to improve the performance. And in particular, in this release, we added some new and improved technology for GPU acceleration. This is a model that's a 10 million degree of freedom model. It's analyzed over a distributed memory architecture. So there are basically 2 boards in the machine. Each board has 2 chips associated with it. Each one of those chips has a GPU unit associated with that. And effectively, the factorization time is substantially reduced, and the total wall time is also reduced. So effectively, we can reduce the simulation time for a 10 million degrees of freedom problem, nonlinear problem, bolt tightening occurring, 48 iterations in all, to something around an hour and a half of solution time. So I want to thank you very much for your attention. I also would like to thank Those users who downloaded the beta release of the product and gave their constructive comments, we've tried to incorporate them as much as we could to produce what I think is a really powerful release of the Marc product, and also a high-quality release of the Marc product. Thank you for your attention, and I think I'm willing to stay on to answer any questions.